All right, I'm going to talk a little bit about nucleophile, electrophile, and score those briefly, and then identifying electron-rich and poor areas in molecules. Okay. All right, nucleophile, something to get used to, okay? Probably going to show up the rest of your organic chemistry experience at UIS. Nucleophile, nucleus is positively charged, phile means like, okay? Nucleophiles like positive charge. The nucleus of atoms, think of them as positively charged, right? That's where our protons are located. Nucleophiles like positive charge. They're attracted to positive charge, and we know that opposites attract. Okay, nucleophile here with a lone pair on it. A lot of the bases we use in proton transfer acid-base reactions were nucleophiles. Electron dense, that want something positive, that like positive, nucleophiles. Okay, they'll often have. I'm just going to write electron dense. They're electron dense and they're attracted to electron poor areas. What are electron poor areas? Electrophiles. Electrophiles like electrons. Okay? All right. So they like negative charge. They're attracted to negative charge. All right? And they are electron poor. So we're going to be dealing a lot with nucleophile attack and nucleophile attack at electron poor areas, areas that may be deemed electrophiles. Okay, let's get into this bottom part here. Identifying electron poor, electron rich areas. Okay. Our first example here in the blue, I have a primary, secondary, or tertiary alkyl halide. How many carbons is that bonded to here? It's only bonded to one other carbon. This is a primary alkyl halide. Okay. If you watched the last video, hopefully you got that. Now this chlorine here, we know chlorine's very electronegative, okay? So we know, and especially compared to our carbons, that around chlorine there is a large partial negative charge that's pulling electron density towards it, okay? Now, when we talked about induction with our cardio rules, remember how we said that the closer that fluorine atom, or the closer that that highly electronegative atom was to where a conjugate base charge was going to be localized, the greater that pull was going to be. The closer we were to that negative charge, right? If fluorine's all the way over here, it's not going to have that greater pull. But if we have fluorine only maybe 2 bonds away, okay, a lot of induction going on there. So, out of these carbons here, chlorine has a strong electronegative pull, and just like induction, it's going to have the greatest effect on what's right next to it. So, compared to these 2 carbons, I have a slight partial positive charge there on this carbon because that chlorine is pulling that electron density away. This is the most positively charged area in this molecule. And it usually will always be the carbon that is adjacent to our alkyl halide. Okay. So I have a nucleophile. Nucleophiles like nucleus. Okay? Nucleus positive charge. These are electronegative, these are electron-rich molecules, species, okay, that are attracted to positive charge. So I have a nucleophile. Where is it going to go? To with a positive charge. Okay. Now we'll get into whether this would be an SN1 or SN2 reaction in a little bit. Okay. But if I had a nucleophile, gonna go to my positive charge. Okay. Chlorine would leave, blah blah blah, leaving group, good leaving group. This would be an SN2 reaction because of the primary alkyl halide. We'll get into that. Right now we're just identifying electron rich, electronegative atom, pretty straightforward. Electron poor because of induction. Okay. Same thing here. We have a ketone. All right. Electron rich area is going to be my carbonyl group. Okay, my oxygen on the carbonyl, large pull of negative charge upward there, causing a partial positive at the bottom. Okay. Where would my nucleophile attack? Right there. Okay. Pushing a bond then up on oxygen. Cool. All right. So yeah, same thing there. Highly electronegative oxygen causing a partial positive charge on that adjacent carbon. Same thing here. Highly electronegative atom. At our end here we have oxygen, partial negative, partial positive on our epoxide there. Okay. I have a nucleophile. It's going to be attracted to one of these. Notice how they're the same carbon, really. I'd have a nucleophile that would attack one of these carbons, and this bond would go into oxygen, just like it did with our ketone. Nucleophiles like positively charged things. Whoa, carbocation. What kind of carbocation? Secondary carbocation here. Nucleophile would attack right there at the carbocation position. It is the most positively charged species. And last example here we have is a carbon with 2 chlorine, 2 fluorine on it. And so yeah, we have a large, yes, we have an equal pull, right? So this would be a non-polar species here because we have equal, okay, equal pull there. Trying to think of the tetrahedral structure, yeah, should have it. Okay. But yeah, even though that electron density is spread out evenly, okay, it doesn't mean that within the molecule it's evenly spread. This would be almost like a donut shape, where the donut would be electron rich and the hole in the middle would be very positively charged. Right here in the middle are carbon, and then we would have all around it our negative charge. Cool. Our electrophile would be attracted to our nucleophile would be attracted to our carbon. Okay. So let's get into SN1, SN2 in the next video. We might do it. Okay.